Hello everybody, welcome into another lesson. So today we are going to talk about the trigonometric form of a complex number. So you're going to have some complex number z equals a plus bi, where this is a complex number in standard form, where a is the constant in the real number system and b is the coefficient of your imaginary number. Together, if we recall from what a complex number is, it's the sum of the real number plus the imaginary number gives you your complex number. So why would we want to convert these to trigonometric form? Well, it's very useful, especially when we go to take powers of complex numbers. Let's say you had something like 2 minus 3i raised to the 20th power. Of course you can use the binomial theorem, but you're going to be there for quite a long time trying to expand this to the 20th power. In the next lesson, we're going to learn something called de Moivre's theorem, which will teach us how to use the trigonometric form of a number to expand these to powers and make our lives a lot easier. It's so much easier than using the binomial theorem. But for today, we're just going to cover some basics. So the first topic is finding the absolute value of a complex number. To find the absolute value of a complex number, all you're going to do is take the square root of your a squared plus b squared. So you take the square root of the sum of your real number squared plus the coefficient on your imaginary number squared. Pretty basic. So let's go ahead here, let's do some examples of finding absolute values. So let's say we're given 6i. We want to find the absolute value of 6i. So we have the complex number z equals 6i. Well, I think it's going to be pretty simple here. If we want to take the absolute value of this complex number, it's just going to be the square root of 6 squared, which would just give you 6. So the absolute value of 6i would be 6. Pretty easy there. Alright, z equals negative 2i. So z equals negative 2i, so to find the absolute value of that complex number, just take the square root of that negative 2 raised to the second power, which would end up being the square root of 4, which would be 2. So the absolute value of z equals negative 2i is 2. Alright, z equals negative 4. So we have a real number, but we're still going to do it with the method of finding the absolute value for a complex number. So you'll just take the square root of that negative 4 squared, which would be the square root of 16, which would be 4. So the absolute value of negative 4, of course, is 4. Alright, so what if I gave you z equals negative 4 plus 4i? There's a complex number, so z equals negative 4 plus 4i. Well, let's find the absolute value of that complex number by taking the square root of that negative 4 raised to the second power plus that 4 raised to the second power, which would end up equaling the square root of 16 plus 16, which would equal the square root of 32. I almost forgot the square root. That'd be very important. Which would break down into 4 times the square root of 2. So the absolute value of negative 4 plus 4i is going to be 4 times the square root of 2. Alright, let's see. Z equals negative 5 plus 12. Not 2. How am I forgetting stuff? Negative 5 plus 12i. So the complex number z equals negative 5 plus 12i. Well, let's find the absolute value of this complex number. So that's going to equal, of course, the square root of that negative 5 squared plus that 12 squared, which would equal the square root of 25 plus 144, which would equal the square root of 169, which would be 13. So the absolute value of negative 5 plus 12i is 13. Let's do one more, and then we'll move on to actually expressing the trigonometric form of a complex number. Z equals 10 minus 3i. So you have the complex number z equals 10 minus 3i. Okay, so let's go ahead and find the absolute value. So the absolute value of this complex number is going to be the square root of 10 squared plus that negative 3 squared, which would equal the square root of 100 plus 9. Of course, is the square root of 109, but let's see if the 109 breaks down. I almost want to say it does, but let's just be sure of that. Nope. Okay, so literally the absolute value of this complex number is going to be the square root of 109. Alright, so that's finding the absolute value of a complex number. Now this is going to tie into what we're about to do next, which is going to be finding the trigonometric form of a complex number. So let's go ahead and discuss that. So again, you have the complex number z equals a plus bi, the standard form of a complex number. Well, this can be rewritten as z equals r times the cosine of theta plus r times the sine of theta times I. And we're in a few segments we're going to get into something called polar coordinates, which are eerily similar to this, but that's not right now. Okay, so how the heck do we find r? How the heck do we find our angles? So r, your radius, is nothing more than the absolute value of your complex number. It's nothing more than that, your r. Nothing more than than the absolute value of the complex number. Now, what about dealing with the angle? So basically you're going to treat this like an x plus y. We know that the tangent of theta is y over x, right? So the tangent of theta is going to be your b over a. That means to find theta, you're going to take the tangent inverse of b over a. So your angle can be found of taking the inverse tangent of your b over a. You just think of it as, because we remember from back towards the beginning of trigonometry that the tangent is your y over x. Even though this is complex, again, think of b like your y variable and a like your x. Pretty much the best way I can help you to remember that. Because tangent's y over x, so then you just take the tangent inverse of your b over a, you'll end up getting the angle. And then your r is simply the absolute value of the complex number. So let's go ahead and do some examples of how to find the trigonometric form of the complex number. Alright, so we have z equals 5 minus 5i. Okay. Well, first thing you want to do, again, I would say, is find your r, which is going to be the absolute value of that complex number. So that's going to end up equaling the square root of 5 squared plus negative 5 squared, which would end up being the square root of 25 plus 25, which would equal the square root of 50, or simply 5 times the square root of 2. So there's your r being 5 times the square root of 2. Now we need to find the angle. So the tangent of theta equals your b coefficient, which would be negative 5, over your a coefficient, which is 5, which of course would give you a tangent of theta equaling negative 1. Well, we need to consider something here. Let's picture this graphically, because we need to identify what quadrant we're in. Though this is the complex plane we're dealing with, it works very similar to the normal real plane. Your a coefficient is positive, your b coefficient is going to be negative. So think of it like your x coefficient, your x number is positive, your y number is negative. What quadrant would that put us in? That put us in the fourth quadrant. Now, what angle gives us a tangent of 1? Just plain old 1. Normally that'd be a 45-degree angle, right? However, since we're going to be in the fourth quadrant, take 45 away from 360, you'll end up getting 315 degrees. Or you could say 7 pi over 4, however you want to write it. It would be the same thing, but we're going to use degrees today just to make life easier. So, how are you going to write this complex number in trigonometric form? Well, it's going to be z equals your r, which is 5 times the square root of 2, times, now it's the cosine of your angle, so this would be the cosine of 315 degrees, plus the sine of 315 degrees, I. And you can leave it like that. In fact, especially when you have a radical for the absolute value of a complex number, sometimes it's best to leave this in factored form. So the trigonometric form of 5 minus 5i is 5 times the square root of 2 times the quantity of the cosine of 315 degrees plus the sine of 315 degrees times I. And we got more. Don't worry, I'm not dumping you off here. Alright. Z equals the square root of 3 plus I. Alright, so we have the complex number Z equals the square root of 3 plus I. First thing I'm going to suggest is you find your R, which is I almost said the amplitude. It's the absolute value of this complex number, which is going to be the square root of that square root of 3 squared plus the coefficient on the I squared, which would just be 1 squared. Well, that's going to equal the square root of 3 plus 1, which is the square root of 4, which would give you an exact 2. So your R in this case is going to be 2. Alright, now we just need to deal with the angle. So the tangent of theta equals 1 over the square root of 3. Well, we need to find the angle. Now keep in mind, treat these again as x and y. You have a positive x and a positive y, you could pretend. So what does that mean? What quadrant? That's going to be in the first quadrant. So they took it easy on us this time. It's going to be in the first quadrant. Now what angle gives us an inverse tangent of 1 over the tangent of theta being 1 over the square root of 3? Well, that would definitely end up being that'd be 30 degrees, right? No, that would end up being 30 degrees. So theta in this case would be 30 degrees. Now we're ready to proceed to writing this number in complex form. So you're going to have your complex number Z equals that R value, which is your absolute value of the complex number. That'd be 2 times the quantity of the cosine of theta, which is 30 degrees. And actually, let's do plus I times the sine of 30 degrees. It might be best to write it this way. So your complex number is going to be 2 times the quantity of the cosine of 30 degrees plus I times the sine of 30 degrees. And if you were to perform these trig operations, you should get exactly this original complex number. All right. Let's do a couple more. Z equals -1 minus 2i. So we have Z equals -1 minus 2i. Well, let's go ahead, start out by finding our R, which would be the absolute value of this complex number. So that's going to equal the square root of that -1 squared plus that -2 squared, which would end up being the square root of 1 plus 4, or simply the square root of 5. So our value of R, which is the absolute value of this complex number, is the square root of 5. Okay, now we need to deal with finding the angle. So the tangent of theta is going to equal that -2 over -1, or simply 2. Well, we have the tangent of theta equals 2, but since, let's pretend again, these are your x and y values, you have them both negative, which would mean this is in the third quadrant. So when we take, one thing we got to know is there is no special angle value that's going to give us a tangent of 2. We're going to have to use the inverse tangent function. But since we're going to take the inverse tangent of a positive number, that's only going to give us a first quadrant answer. Our angle really lies in the third quadrant, so we'll have to add 180 to whatever result we get. So we're going to get a decimal approximation of this. So let's go in here. Let's take the inverse tangent of 2. For your first quadrant angle, you get about 63.43. If you add 180 to that to get you into the third quadrant, you get approximately 243.43 degrees. So your angle is approximately 243.43 degrees. Now to write the trigonometric form of this complex number, it's going to be your r, which is the square root of 5, times the quantity of the cosine of 243.43 degrees, plus I times the sine of 243.43 degrees. So the trigonometric form is z equals the square root of 5 times the quantity of the cosine of 243.43 degrees plus I times the sine of 243.43 degrees. Let's do one more of these, then we're going to work backwards, which would actually be pretty easy. So let's see here. Z equals, let's see, 3 times the square root of 2 minus 7i. So z equals 3 times the square root of 2 minus 7i. Okay, so first thing you want to do, again, find your value of r, which is going to be the absolute value of this complex number. So that's going to, of course, be the square root of the quantity of 3 times the square root of 2 squared plus that negative 7 squared. Alright, so 3 squared is 9 times 2 is 18. This would turn into the square root of 18 plus 49, which would simply give you the square root of 67 with no further way to reduce that. So your r is going to be the square root of 67. Now, let's go ahead and find your angle. So the tangent of theta is going to equal your b value of negative 7 over your a value of 3 times the square root of 2. Well, let's see what quadrant we're looking at here. So, pretend this is your x and y. Positive x, negative y puts you in the fourth quadrant. Now, when you take the inverse tangent of this, you'll get a fourth quadrant angle, but the problem is inverse tangent is only defined for the range between negative pi over 2 and positive pi over 2. So you'll get a negative angle that you're going to have to add to 360 in order to get the answer from 0 to 2 pi. So take the inverse tangent of, well, no, why don't we do this first. 3 times the square root of 2, take negative 7, come on, cooperate with me. Alright, now take the inverse tangent of that. So the negative angle, you get approximately negative 58.78. If you add 360 to that, you'll have an answer between 0 and 2 pi. You'll get about 301.22 degrees. So the angle we're looking for is about 301.22 degrees. Now that we know r, we know theta, we can proceed. So the trigonometric form of this number is going to be that r, which is the square root of 67, times the cosine of 301.22 degrees plus I times the sine of 301.22 degrees. So there's the trigonometric form of this complex number. Alright, so there's converting complex numbers in standard form to trigonometric form. Let's just do a few where we work backwards. So we're actually going to work backwards for once, and it's actually, I think you're going to see, so much easier than what we just did. So z equals 2 times the quantity of the cosine of 120 degrees plus I times the sine of 120 degrees. Alright, so this time they give you the trigonometric number in complex form. We want to convert this back into standard form. That's actually a piece of cake, because you'll keep your 2 outside here for a minute. Now, what is the cosine of 120 degrees? Well, that's a 60-degree angle in the second quadrant. So that would actually end up being negative 1/2 in this case, plus I times, what's the sine of 120 degrees? That's the sine of 60 in the second quadrant. That'd be the square root of 3/2. Now you just take everything, multiply it by 2, you'll get that z equals negative 1 plus, I'm going to write it as I times the square root of 3 because I don't want it to look like my i's under the radical. But that was pretty simple. Z is going to be equal to negative 1 plus I times the square root of 3. All you got to do is just do the basic trig operations and you got your answer. Let's do a few more of these. All right. Let's see. 3/4 times the quantity of the cosine of 315 degrees plus I times the sine of 315 degrees. Alright, so the trigonometric form of a complex number is given 3/4 times the cosine of 315 degrees plus I times the sine of 315 degrees. Well, let's go ahead and just do the operation. So leave that 3/4 on the outside of the parentheses. Now, what is the cosine of 315 degrees? That's just a 45-degree angle in the fourth quadrant, which would actually give you a positive value. Normally, the cosine of 45 is the square root of 2/2. So we'll put that in, plus you're going to have I times, what's the sine of 315 degrees? That's a 45-degree angle in the fourth quadrant. Since it's the sine, it'll be negative square root of 2/2. So now we'll just do the multiplication. you'll end up getting 3 times the square root of 2 over 8 minus 3i times the square root of 2 over 8. So in standard form, this should be 3 times the square root of 2 over 8 minus 3i times the square root of 2 over 8. Alright, let's do one more, but it won't be quite as nice. We'll end up having to use a decimal approximation for it. So let's say we're given three times the quantity of the cosine of 18 degrees and 45 minutes plus I times the sine of 18 degrees and 45 minutes. So yeah, definitely not a special angle. I think it's plain to see we're going to end up with a decimal approximation. But what might help is if we convert that 45 minutes into a degree with a decimal point. Well, 45 degrees is 3/4 of a degree. So this can be rewritten as 3 times the cosine of 18.75 degrees plus I times the sine of 18.75 degrees. Now, I'm going to take my initial result to 4 decimal places, but I'm going to round the final result to 2 decimal places. That way I get the most accuracy. So, let's do, of course we'll have the 3 on the outside, but let's find the cosine of 18.75 degrees. That's approximately 0.9469. Plus, we'll take I times now the sine of 18.75. That'd be about 0.3214. So we can do a final answer now. Just take everything, multiply it by 3. So 3 times 0.9469, that's about 2.84. So you would get about 2.84, not 284, yikes. 2.84 plus, let's take 3 times 0.3214. That'd be about 0.96 times that I, of course. So the approximate form of this complex number is going to be about 2.84 plus 0.96i. I think we'll call it good for this lesson. Next lesson, we're going to actually multiply and divide complex numbers using the trigonometric form. There's formulas for that to make your life easier, especially for division. Multiplication, you're going to think it's overkill, but division, it's definitely going to help us. So I hope everyone has a great day. Take care.